Hi there, this is David Roach. I'm going to talk to you today about our new book on quantum economics, which is called, fun enough, QE for short, and which will be published in a couple of weeks. Now, the book deals with the history of quantum economics, what it actually theoretically says, and it also then goes on to lay out for you the significance of quantum computing on the ability to put quantum economics into practice. Now, the title, or if it had a title apart from QE, of this book would be It's Not What You Think, But How You Think It. Creative writers, both poets, philosophers, have long questioned how we deal with time, space, and reality. We are too much like oysters observing the sun through water and thinking that thick water be the thinnest to bear, said Herman Melville in Moby Dick. T.S. Eliot put it like this: time present and time past are both perhaps present in time future, and time future contained in the past. That's from Bernd Norton in the Four Quartets. But quantum economics has proven what literature said was true. The subatomic world of which our world is made up obeys laws that contradict many of our perceptions. If you take subatomic particles, they can be in multiple places at once, called superposition and wave theory. They can be linked across time and space and communicate with each other at something like the speed of light, which is called entanglement. This much is proven scientifically and by observation. To show that, I need to show you the presentation. Now, this is wave theory in the presentation, and what it does is, to the left of that blue particle splitter, you have subatomic particles which can be in any position. It's not they either are on the bottom blue line or the top blue line, they are on both at the same time. And it's not that they are to the right or to the left, they are both at the same time. So it is not like anything we have ever thought about before, because our interpretation of the world is based on big objects. Now, big objects are houses, trees, kitchen tables, spouses, maybe your Lamborghini, or in my case, my humble bicycle. They're big, they have mass, they have slopes of velocity, and they are warm. So they cannot be observed like particles in this particular diagram of wave theory. Nevertheless, all of these big objects are made up of quantum particles. Now, let us think about this for a minute. Before the subatomic particle, let's say an electron, is measured, that is to the left of the particle splitter, it is not in any one of these positions, it is in all of these positions at the same time. Once it is observed, which is when it goes through the particle splitter, then it becomes a singular value. The certainty is that what you are observing is now going to be its history. So the difference between superpositioning, being in many places at the same time, and entanglement, being able to communicate across space and time, is something which belongs purely to subatomic particles before they are observed by passing through a particle splitter. Big objects are made up of these particles, but they do not seem, to our perception, to behave like that. All of our forecasting tools, for whatever macro variable you wish to conceive, are based upon the seeming stability and predictability of big objects. I will give you a very concrete example. Euclidean geometry, used to observe and measure the world since the ancient Egyptians. The isosceles triangle has two legs which are the same length and angles which make up to 180 degrees. But that only holds as long as they are within our perceived reality. Once you extend them into the curved space-time of Einstein's relativity, this no longer holds. The isosceles triangle can have two legs the same length, but it will not have angles which add up to 180 degrees. They will add up to something completely different because of the nature of curved space and time. Now, we do not know how to reason outside the comfort zone of big objects, or even picture multiple dimensions beyond 3. But big objects are not stable because they are made up of particles which obey quantum rules. I'll give you an example. The sun is probably big enough for you to qualify as a big object. And the sun heats us, without which we would all wither away with cold rather than wither away with global warming. But the sun only manages to heat us, provided something happens in quantum physics, which is called quantum tunneling, which is the ability of a subatomic particle to be on both sides of an impenetrable barrier at the same time. This allows nuclear fusion to happen on the sun. Nuclear fusion releases the energy, which creates the heat, which heats us without diminishing the size of the sun. If it was a normal process, not nuclear fusion, but just burning, the sun would burn away and we would shrivel away from cold. Let us now apply the fuzzy magic of quantum physics to the forecasting world. We have to get rid of some dross first. First comes the rule of big committees. The collective intelligence making a forecast does not increase with the sum of the people involved, but the sum of the people involved divided by the square root of the number of people. So there is an ensured convergence towards mediocrity. The US Fed has 22,000 employees and doesn't get its forecasts right. The Bank of France has 10,000 and doesn't even make any forecasts. And the ECB, God help it, has only got 4,000. And they have a track record on forecasting, which is worse than none. Take Jackson Hole. All the academic papers presented at Jackson Hole are 100% based on the historic correlation of observed variables. But those variables do not explain the future. Consensus forecasts can never predict a crisis either. And the reason they can never predict a crisis is because crises depend on surprises. And consensus forecasts, by definition, exclude all surprises in order to make them coherent with themselves. Let us have a look at this. This is the forecast of the Fed fund rates made by tens of thousands, if not hundreds of thousands, of worthy individuals who earn their living doing so. The big blue line is what the Fed funds rate actually did. And little spidery lines shooting off it in all sorts of directions are what the forecasts were at any given point in time. So the period covered is January 2006, 2023, and you can see immediately that in most of the cases, the direction of the forecast is just plain wrong. It is in the wrong direction, and the US Fed goes off in another direction. And in other cases, when there is an established momentum in the US Fed funds rate, the forecasts go in the right direction, but never precisely. And the reason they go in the right direction is because that's what consensus committees do. They look at the past, they look at established momentums, and they extrapolate them into the future. And that is exactly what goes on here. But of course, it does not add 1 penny to your portfolio or 1 gram to your wisdom. They are just wrong. I will give you another example. This is a forecast based on historical correlations made in 1914 of the speed at which man could move. Looking into the past, from man moving on foot to the Model T Ford, and then extrapolating those variables in a very sophisticated multi-regression model, came to the conclusion that today, man would be moving someplace between those two dotted lines with a degree of confidence of over 80%, as they're based on standard deviations. The reality is, of course, man is now moving at the speed of the little dot marked now. And the reality is the blue line. So again, you can see that basing your forecasts on historical correlations is not going to get you anywhere, which is where quantum economics come into the picture. Let's picture, first of all, traditional forecasts like this. Here we have what we call a quantum quilt. So we have 4 independent variables: monetary policy, geopolitics, and fiscal policy, just picked out of a hat, really, and they're going to forecast the dependent variable called markets. But of course, within the confines of those 3 independent variables and 1 dependent variable, there are lots and lots of little squares called Paul Klee magic squares, which are filled with variables which actually determine the geopolitics, the monetary policy, and the fiscal policy. It may be the degree of mental acuity of the US president, or indeed the European leaders of state, which set geopolitics. It may be your favorite measure of monetary policy, which sets monetary policy, or sets inflation, which sets monetary policy. And it may be the size of a budget deficit here or there, or some places that matters, that sets fiscal policy. So inside this quantum quilt, there are lots and lots and lots of little squares full of variables. And when you make a consensus forecast, you make sure that all those little squares tie up nicely. And in turn, they set, through historic correlations, the values of the 3 independent variables of monetary policy, geopolitics, and fiscal policy, which in turn give you a market forecast, which you write down in succinct form in between 50 and 150 pages. And we are at the time of the year when these things are thudding, at least metaphysically, across your computer desk. And they all say the same thing while pretending to say something different. And within a few months, or at least within a quarter or 2, they have been proven utterly wrong. So how do you actually go about forecasting? Well, the answer is you move to quantum economics, where you start with the little squares, the little magic rectangles of Paul Klee. This may be 20, it may be 30. Actually, there are millions of variables which act in a disruptive fashion, consistent with themselves. For instance, the renminbi can go down, but the US dollar can go down at the same time. And US interest rates may move down while renminbi interest rates move sideways. And theoretically, in our historical correlation models, that can't happen, but they do happen. But what happens to each of these disruptive variables is consistent with itself, but not with each other, and not, of course, with the big independent and dependent variables which form the outer perimetry of the quantum quilt. But the reality is, unless you can forecast the disruption of the magic rectangles, then you cannot forecast the dependent variables, and you cannot forecast the independent variables which lie at the edges of this quantum quilt. Now, you can make up a system within your worthy organization, which I am sure can simulate the quantum economic process of forecasting, the disruptive variables, the decoherence which occurs when these variables do disrupt. You can simulate that by having a couple of, maybe 2, maybe 3, maybe just 1 creative person in a room. But you cannot, and your computers, classical computers, cannot simulate or deal with the complexity of all of the variables which determine economic behavior. Economic behavior is, of course, simply the statistical expression of millions of variables which describe human behavior and the consequences of that human behavior, and indeed disruptive variables outside the patterns of human behavior altogether, which nevertheless impact it. This is a sense of the inability to put quantum economic forecasting, which deals first and foremost with the disruptive variables in their millions, at the center of the process, because the complexity cannot be coped with today's computers, and even with the creativity and genius of people who are creative and are genial and are not simply dull consensus forecasters. You can't do it. Where you will be able to do it is when quantum computing starts to take effect. Now, quantum computing is going to be there in a matter of a few years. It will allow computation of the quilt's internal cells in all their millions and billions, and their disruptions as the source of forecasts. Now, this process will not be based upon the historic observation of variables or on their historical correlations, but upon the future feasible values of the cells themselves. There have been examples of this, such as testing mRNA vaccines against COVID, where historical information was of no value, but the actual current pattern of DNA of human beings, which was available in anonymous formats and in masses of big data, did allow for testing in a way which the forecast results allowed for the vaccines to be approved. But of course, you are not dealing with a historical series of data at all. So that, plus the fact that neural network computing, which resembles something much closer to how the human brain works, is also starting to become a reality, will allow forecasting to move forward and away from historical variables and the obsession with past data as a source of thinking about how we are going to exist in the future. Let us, however, move on. Let us consider what this actually means in quantum computing terms. This is a diagram of Moore's law of computational power. And what it said was that every 2 years, the number of semiconductors on a silicon chip would double, and thus computational power would increase exponentially. Now, that has happened, and we have actually, in computing power, in terms of classical computers, reached the equivalent of the size of the brain of a mouse, which is the red dot. But unfortunately, we're running out of momentum. And the reason we're running out of momentum, which is shown by the green line, which shows the process of Moore's law, the exponential increase in computational power, is coming to an end. The reason that is happening is because, number one, it's getting more and more difficult in terms of physics and the nature of the qualities of the actual material to put more transistors on a chip. You can only etch so much onto a silicon wafer and you reach the limits, and we're reaching the limits. The second is it's got far more capital intensive to produce the sort of chips which are at the leading edge. And we're talking about sub 5 nanometer chips. It requires many, many, many more dollars to get there than it did in the past. It also requires a lot longer time to scale up production to the size which is needed in order to put chips into our 5G mobile networks, our latest weapon systems, and I can go on and on. So it has become a much lengthier, more expensive process, which is slowing it down. There are also geopolitical factors involved, and the fact that making silicon chips is extremely environmentally degrading and requires a huge amount of water, where certain centers of chip making, semiconductor fabrication, like Taiwan, are actually in trouble as regards the supply of water and the environmental damage which is being done. But all is not lost. What is going to happen is that quantum computers are coming along, and for reasons unrelated to the number of chips, number of silicon, number of semiconductors you can put in a silicon wafer, you will be using qubits, which are the quantum equivalent of bits on a classic computer, but far bigger, far larger, far faster. These bits will allow for computational power to continue to grow exponentially, unrelated to Moore's law. So effectively, we have seen nothing yet. Okay, now how does this actually work? If you think about it, quantum computing matches reality in ways that classic computing and forecasting can never do. That is why it is essential to quantum economics to have the power of quantum computers as its tool. There are really 7 factors. First is quantum computing is quantum physics. It is not like quantum physics, such as it would be if you sat in a room with a bright person and made up a system of forecasting which focused on the disruptive variables in the center of the quantum quilt. That would be simulating quantum physics, but it would not be quantum physics. Quantum computing is, however, quantum physics. Quantum computing works by superpositioning, i.e. multiple simultaneous positioning, as in wave theory of qubits. And it also works by entanglement, which is what Einstein calls spooky action at a distance, and we describe as communicating across space and time at something like the speed of light. Thus, quantum computing can behave randomly while being in a defined physical state. In classical computing, bits are either 0 or 1. That's how a classic computer actually works. The electrical charge going through the computer transforms the bits into 0, the registers into bits of 0 or 1. In quantum computing, the qubits are both 0 and 1 at the same time. In binary logic, things are or are, they are not. Let me say that again without stumbling. In quantum computing, things are both they are and they are not at the same time. But that actually means that you take Schrödinger's cat, it is dead or alive under normal classic computing. In quantum computing, it is both dead and alive at the same time. And that problem is only resolved with certainty when the box is opened and we observe, as when the particle, subatomic particle, goes through the splitter. When it is observed, it becomes the cat, either dead or alive. But once in the quantum computing process, it is both dead and alive. So things are and are not at the same time. Qubits only assume a defined classical value after they are measured, as in the case of opening the box and seeing if the cat is dead or alive. Let me put this to you in a way which is more tangible. Take the problem or the puzzle of a maze. You can go to Hampton Court and wander around a beautiful botanical maze, or you can play a maze game on your laptop or computer screen. The game is to get through the maze, from north to south or east to west. Now, a classic computer will try one road, hit a hedge, come back, try another way, hit a hedge, come back and find a way through eventually, and then come back and exhaust all the paths and the combination of paths through the maze until it has found all the ways through and all the ways that don't go through, which it will produce as a classic computing result. Quantum computing doesn't work like that at all. It goes through the maze simultaneously, every single path at the same time, and comes back to you with the results in a nanosecond. Now, that tells you what the maze game tells you what quantum computing actually adds to the world in which we are going to use quantum economics as a means of forecasting where humans are going. It adds the ability to cope with huge input complexity. All the paths through the maze at the time, not one at a time. It simultaneously computes all of the pathways through the maze. So capacity. And it produces the results of those pathways, all of them, with incredible speed. So it adds speed. So quantum computing, complexity, capacity, and speed. And that is why it is essential to the quantum economic reasoning, which starts computing the future of whatever variable you are looking at. They needn't be economics or markets, but I'm just taking that as an example. What it does is give you the ability to deal with a huge amount of variables in all their complexity, to simultaneously test their combinations and results, and to do that at a speed which a classic computer simply cannot do. Now, this is what a quantum computer looks like. So we have to admit to ourselves that we're not going to be putting it in our briefcase anytime soon, or bringing it home to do homework, or work from home, as homework is now called. It's a big thing, which looks like something that was invented in Frankenstein's laboratory. So how do we work with it? Well, here's how we work with it. The gateway to quantum computing is actually, for the foreseeable future, going to be through classical computing. That is where the results come out, and it is where the input goes in. This is stored in its complexity in A1, artificial intelligence, neural network, which forms the feeding station and the storage of results from quantum computing, where all the computing is done. So that is essentially what we're going to be working with for the foreseeable future. So if you access your quantum computer from your home workstation, or maybe it's your permanent workstation like me, then you will be using a classic computer message, not only to put in the data or to load it, or to put in the questions you want answered or the variables you want tested, but you will be using it to interpret the results. Because what happens is the qubits in all their decode, once they pass through the equivalent of the splitter, once they are measured and observed, they become single values, and they are then downloaded in a format in which classic computing can actually make them visible and interpretable to your small, and mine even smaller, brain.